Okay, thanks, Adolfo. All right. Well, hi everyone, and thanks for joining for this last lecture of the series. Today is going to be a little bit different from the first two lectures because I'm planning on focusing a little bit more on technique, a little bit more on numerics, but mostly from the point of view of how you can use numerics to to see if you might have a fractional quantum Hall state as a ground state in your system. So that's definitely applicable to moire systems. And in fact, I've already shown some of this numerical data, but I'm going to go into a little bit more details, and I'm going to explain a little bit more how we do this. And before I go into that, I would like to acknowledge the people that I've had the pleasure of working with on these moire superlattices, especially Cécile at MIT and grad students in his group, or former grad students in his group in some cases, Ji Wandong, Yari Zhang, who's moved on after that to be a postdoc at Harvard, and Jenny Crawford. So yeah, this is just a short reminder of the overall outline of the lectures. We started, overall we talked about correlated insulators in moire superlattices, both at integer and fractional filling. And today is going to be focused on fractional filling fraction, and more specifically fractional Hall conductivity, by looking at numerical signatures of fractional quantum Hall phases. And I'm using that term in a broad sense, meaning, it doesn't have to be in the continuum, it could be on the lattice as well. So this is the outline for today. So again, I'd like to start with some motivation. So I've given lots of motivations, I think, to work on these phases of these fractional quantum Hall phases, but I'd like to talk about them in the broader context of topological order a little bit, as it is a very important physical aspect of why we're interested in these phases in general. And then I'll talk about two types of ways of diagnosing fractional quantum Hall states numerically, mostly through spectroscopic methods, from the degeneracy of the ground state and Quasihole excitations on the torus. So that's a method that mostly applies to exact diagonalization. And finally, through the edge spectrum. So that's a method that applies in various contexts, but especially well in the context of GMRG. And you don't have to know anything about these numerical methods to follow the lecture. That's I'm not going to be basing the lecture much on technique, really. Yeah, so topological order. So what do we mean when we say that? So broadly speaking, topological order corresponds to an incompressible quantum phase or a gapped quantum phase. And I'm going to focus exclusively on two-dimensional phases. And I'm starting with that definition because so it's going to be much more specific than that, of course. But I'm starting with this because it's important to distinguish topological order from the concept of a topological phase in general. So topological order is a form of topological insulator in the sense that there is no local order parameter that would help you characterize this phase. But it is distinct from a topological insulator in the topological band point of view, because when you have a state that has topological order, you cannot write it as a product state in any single particle basis. So, for example, a Chan insulator doesn't have topological order in that sense, because you can write it down as a product state, meaning as a by just filling up a chain band and writing down the Slater determinant corresponding to that. And what's very specific about phases with topological order is that their excitations are fractionalized. They are anyons, so they are neither bosons nor fermions. And what this means is that their statistics is in between, is not bosonic or fermionic, but when you exchange two anyons, your wave function is going to acquire a non-trivial phase, exponential I theta here. And in some cases that are even more complex, a phase is not enough to describe the exchange statistics, but you have to use a matrix. And that's the situation where, even though you've specified the position of all the anyons in your problem, there's still a degeneracy. And then doing an exchange in that, among those anyons, doing an exchange operation is going to correspond to a rotation in that manifold that is characterized by a matrix Q. Okay, but we don't really need that. I'm going to talk about abelian phases only, but that's a big motivation. Being able to understand and realize phases that have abelian or non-abelian anyons is a big motivation to study topological order in general and fractional control phases in particular. So I can maybe give you a few examples of topological order. And a very famous one is found in the Torus code, and it's very convenient because it's an exactly solvable model, and we have very few models realizing topological order that are exactly solvable. So this one is very convenient for this, but it's a bit of a toy model, so it doesn't apply directly to materials. If you want a more realistic Hamiltonian that corresponds to a solid material, for example, then you're going to need strong correlation, and for that you're going to need to do numerics. And well, the first example of topological order in an actual, realized system is the fractional quantum Hall effect that we've talked about a lot yesterday. So it arises when you have a strong magnetic field going through a two-dimensional electron gas, and it's characterized by a fractional quantum Hall conductivity. So it's a chiral form of topological order, and it has broken time reversal symmetry because, well, since the Hall conductivity is not zero. And most basic example of fractional quantum Hall effect is the 1/3 fraction, which has Hall conductivity equal to 1/3 times the square over h, the quantum of conductance. And the excitations for this phase are anyons, which have a charge E over 3 and an exchange statistics equal to 2 pi over 3. And just to be very general, we can also cite another example, which is the example of quantum spin liquids. So not all quantum spin liquids have topological order, but some of them do. And we have examples that correspond to the same type, the same universality class as the Torus code. And there are also examples with the same universality class as the fractional quantum Hall effect. So we have very diverse physical systems that may realize topological order. In all cases, if we want to study them, they have the Hamiltonian has strong correlations, so it's a hard problem that requires numerics, which is already a motivation. But focusing on the fractional quantum Hall effect more specifically, what are the motivations to do numerics with it? Well, there's a really long history of using numerics to study the fractional quantum Hall effect, and it's been very successful at helping us understand this phenomenon. And well, so first of all, in the continuum, to understand its topological order. So, for example, yesterday I talked quite a bit about the Laughlin wave function and about the fraction 1/3 of the fractional quantum Hall effect, and I said that the fractional quantum Hall effect at 1/3 is very well captured by this Laughlin wave function. And one of the reasons we know that is because we've been able to do some, for example, some overlap calculations and other things that have convinced us that the ground state at nu equals 1/3 is well described by the Laughlin wave function. And other proofs of topological order, such as the measurement of a fractional charge and fractional statistics, experimentally came afterwards. Other things like knowing what is the value of the gap or the value of the correlation length in the fractional quantum Hall state, those are all things that we know thanks to numerics. And the second motivation for doing some numerics in the fractional quantum Hall context is to try and realize it in the absence of a magnetic field. So that's in principle feasible if you have a Chern band that provides you the intrinsic topology that you need and that removes the need for a magnetic field. Magnetic fields in general are quite impractical, and there are reasons to want to get rid of them. And one of them is to try and proximity couple the edges of a fractional quantum Hall system with a superconductor. And of course, the superconductor is not going to like it very much if you impose a very strong magnetic field. So this type of this type of project is one of the motivations for to try and realize fractional quantum Hall state without a magnetic field. And again, to make contact with the things that I talked about in the past lectures, we don't know how to do this yet, but I think the arguments from numerical calculations have motivated experiments that have really shown a lot of progress in this field. And so so we have example of fractional Chern insulators, so fractional quantum Hall states requiring a lattice, but with still a non-zero magnetic field. And I talked about two of them. One of them was realized in Andrea Young's lab. And basically the fractional Chern insulator states arises around 25 to 30 Tesla. And much more recently, there was evidence in a different sample of a magic angle twisted bilayer graphene aligned with hexagonal boron nitride of a fractional Chern insulator at much lower fields. So this is a field where there's really tremendous and super impressive experimental progress. Well, I hope that things can go even further, and maybe numerics can motivate that a little bit as well. Okay, so what are signatures of topological order, and more specifically of fractional quantum Hall physics? So when we talk about numerical signatures, very often, as a general principle, it's good to try and find bulk signatures. The idea being that you want to minimize finite size effects. And that's because when you're doing a many body calculation, very often you only have access to a small number of system sizes, and those sizes are going to be super limited due to the exponential growth of the Hilbert space with system size. and no matter what method you're using, finite size is probably going to be a limitation. So to minimize finite size effect, it's good to use a geometry with edges, without edges, sorry. That has that's a kind of a generic principle. This is especially true for topological phases, because if you don't have any edges, then you have a fully gapped system, and numerically that's good for numerical convergence. So in the context of exact generalization, that often means using the torus geometry. Actually, in fractional quantum Hall physics, we also use the sphere geometry, but so that's not very relevant in the context of lattice systems. If you have a lattice system, it's the most convenient is to have periodic boundary conditions. That's the torus geometry. The additional advantage of this geometry is that you have the maximum amount of spatial symmetries. So you can use the corresponding quantum number, the momentum on the lattice, for example, to block diagonalize the Hamiltonian. So that will reduce the size of the blocks when you diagonalize the Hamiltonian within a restricted Hilbert space, restricted to one quantum number. The other possibility is to work with the cylinder geometry. If you, in some cases, you can work with an infinite cylinder, which means just that you're using a translationally invariant ansatz. And that's going to be the case if you're doing, if you're using the density matrix renormalization group, DMRG. And in fact, an infinite cylinder has the same topology as a torus, so it's also a system that doesn't have any edge. So within all these systems, the main methods are going to be to look at the spectrum, most often the energy spectrum, but it could be an entanglement spectrum as well, as I'll discuss in the lecture. And you can also compute directly some observables. In the fractional quantum Hall context, the most obvious observable to look at is the Hall conductivity. So you can also compute the Hall response in this system. But in the interest of time and to keep this lecture self-contained, I'm going to focus on spectroscopic signatures of the fractional quantum Hall effect. And let me start with some signatures on the torus geometry. So signatures that are best suited to exact diagonalization. So generically, it can be shown that the degeneracy of the ground states on the torus is equal to the number of topological sectors. As an example, for the Laughlin 1/3 states, there are 3 topological sectors, which correspond to the vacuum, which has charge 0. So the vacuum is always included among the topological sectors. Then you can have one quasi-hole, which has a charge E⁻3. And then you can add another quasi-hole, and that's going to have a charge 3/3. If you add an extra quasi-hole, you form a whole charge E fermion, so you're basically back to the vacuum. So there are 3 topological sectors. So what's expected in the thermodynamic limit is to have a 3-fold degeneracy of the ground state. Additionally, you expect a gap to higher energy excitations because those phases are incompressible. And you don't have any edges, so there are no edge states within the gap. So here is an example that I think I already gave yesterday. So this is the quantum Hall effect in the continuum. The Hamiltonian that I'm using is the Coulomb interaction, projected onto the lowest Landau level. And here I'm showing the low energy spectrum for 8 fermions and in 24 flux quanta on the torus geometry. And so I'm using the center of mass momentum here as a quantum number to label all of my eigenstates. So which means I have used that quantum number to block diagonalize the Hamiltonian, and I'm doing one diagonalization for each value of the center of mass momentum. And as noted yesterday, and as is very clear here, this ground state is threefold degenerate. So this is the ground state here, highlighted in blue, and it has a gap to higher energy excitations. Yeah, so the good thing about this this method is that it's universal, right? So it should not depend on the Hamiltonian, and so you can use it to diagnose a new Hamiltonian. For example, if you don't know what is the nature of the ground state of this Hamiltonian. And that can be the case if you have a lattice model with a Chan band and some interaction, and maybe it is a finite bandwidth or something like, or non-homogeneous Berry curvature. So you cannot know for sure just by looking at the Hamiltonian whether the ground states will have topological order or not. So you can use the same method to do that. Was there a question?
Yeah, I think can the usual counting of excitations in the locking state be seen with ED?
Yes, if I understand the question correctly, this is what I'm going to talk about next in the next few slides. So I'm going to answer that very soon.
Thanks.
Yeah, so right now I'm talking only about the ground state when I'm exactly at filling 1/3. But then in the next slide, basically, I'm going to be adding quasi-holes in my system and looking at the degeneracy of the ground state there. And I think that's exactly, yes, that's exactly what you can do with ED. Yeah, so here I'm using the model from yesterday and from so the magic angle twisted bilayer graphene model with an added mass due to alignment with hexagonal boron nitride, which means that I have a conduction band that's separated from the valence band by a gap. So I have a churn band, and I can project the Coulomb interaction onto the conduction band. And here, for the purposes of pedagogy, I'm assuming spin and valley polarization, even though we know that might not be the case in the realistic system. So I'm considering 10 fermions on 30 moire unit cells. And so this is the low energy spectrum that I showed yesterday, but probably a little bit fast. So this is low energy spectrum. Again, I'm labeling all my eigenstates with a momentum. And here you see that I have a linearized momentum. So on the lattice, I have kx and ky quantum numbers. So I could represent the spectrum in this 2D space, but to avoid having a 2D a curve plot or something like this, I'm just linearizing it to have everything on one line. So those are my 3 almost degenerate eigenstates separated by a gap from higher energy excitation, which is a sign that I'm in the same phase as the Laughlin 1/3 state. And something that's very important with any numerical method, any finite size calculation is I cannot trust what I get from just one size. I need to do the calculation several times for several different system sizes. and compare the results. So here I consistently get this threefold quasi-degeneracy with a gap that's okay, that depends a little bit on size, but seems to remain finite as I go towards the thermodynamic limit here. So 1 over ns is 1 over the number of moire unit cells. And in red is the splitting of this degeneracy. So in finite size, there's no reason why the degeneracy should be exact. It's only exact at the thermodynamic limits. Because the sizes are a bit small, within hexagonalization, it's hard to see that it goes exponentially to 0. So we're just happy enough to see that it remains small and it remains much smaller than the many-body gap. So let's now move on to quasi-hole excitations. So we know in the fractional column hole effect that quasi-hole are non-trivial anionic excitations, and that's going to have consequences for their degeneracy that we can diagnose through exact generalization by looking at the energy spectrum when we have quasi-hole in the system. So to add one quasi-hole, we add one flux quantum. So again, I'm taking the case of a 1/3 Laughlin state. So I've shown again the 1/3 case. So like I'm back to the continuum now. So this is 8 electrons in 24 flux quanta. Now I'm adding one quasi-hole, so I'm adding one flux quantum. And this is now the energy spectrum that I am getting. As you see, it's a bit different. So its main features is that I still have a gap, but now the ground state, instead of being threefold degenerate, it has a degeneracy 25. And if I add two quasi-holes, I have a much more complex, much more complex spectrum, still with a gap, and actually 117 states below the gap. Right, so those are the main features, and we can actually understand those numbers, and we can predict them for at least for the Laughlin quasi-hole excitations. And we can predict them through Haldane's fractional extrusion principle. So this principle is it's a principle that states that the degeneracy of quasi-hole states is given by the number of configurations that satisfy a generalized Pauli principle. And when I say a KR Pauli principles, it means that I should have no more than K fermions in R consecutive orbitals. So I'm going to give an example right away to show what that means. Again, using the Laughlin 1/3 example. So for the Laughlin 1/3, K equals 1, R equals 3. And let's start with the ground states. So I'm starting to be as simple as possible. I'm using 2 fermions. And first of all, I'm going to consider 6 flux quanta. So I have a 1/3 filling fraction. So I should find back, I should find the threefold degeneracy that we know there is for the Laughlin state. So the way to read those configurations is the following. So I have a number for each Landau level orbital, and the number just corresponds to the occupation of this Landau orbital. And 1/3 exclusion principle means that if I have a particle here, I cannot have more, I cannot have another one here or here. And because I have also periodic boundary conditions, because I'm on the torus, I can also not have one here or one here. So the only option is to put the second fermion here. And I can also translate that whole configuration using the periodic boundary conditions. So I have in total 3 configurations that satisfy the 1/3 no more than one fermion in 3 consecutive orbitals principle. So you have 3 states, and energetically that would give me this, and that's of course a super simple spectrum because the Hilbert space is super small for this case. Let's now add one quasi-hole, and that's done by going from n phi equals to 6 to n phi equals to 7. So now I have one more orbital in my sequence here. So I have added a 0 at the end. Compare, if I take the first ground state here, I've just added a 0 at the end. I've added a quasi-hole at the end. And then the degeneracy of this quasi-hole is just going to be associated with where exactly I put this quasi-hole. So I'm going to get 7 of them, which is the number of orbitals in total. And that's going to become more complex as I add more quasi-holes. And energetically, that's again what I get. Those are the 7 states here, and then you have a few of the states there. So now, very importantly, I should emphasize that this is just a counting principle. So that's super powerful that we can predict this number of states. If you want to know where that comes from, that's related to counting the number of polynomials that have a given vanishing property. So in this particular case, you're counting the number of polynomials that vanish with power 3 as you bring 2 particles to the same position. Remember that the Laughlin state is Zi minus product of Zi minus Zi to the 3. So it satisfies this. And that's a little bit more complex when you're on the torus geometry, but basically the argument, more rigorous arguments can be written down on the plane geometry using those polynomials. But those are not eigenstates. Okay, so those configurations, each of them, they are effectively, they're product states, right? If I'm just looking at one of those configurations, it's a product state. I've just put one particle in the first orbital and then another particle here. And the Laughlin, that's not the Laughlin state. The Laughlin state is a sum of many such configurations. And actually, they're not all included in there. So it's much more complex than this. But okay, it's a counting principle and it works. Right, so now going back to my more complex case, I can do the same thing, I can write a small script that tells me how many configurations are there with 8 particles in 26 orbitals. And if I only keep those configurations where there are no more than 1 particle in 3 consecutive boxes, and that's going to give me 117, which is exactly the number of states that I have here. So I can use that, as a way to diagnose a fractional quantum Hall state. Now, it's nice. I can go even one step further, and instead of adding quasi-holes to my system by changing basically the Hilbert space, because I'm adding a flux quantum, I can also do it without changing the Hilbert space by from the ground states directly, the Laughlin ground states, well, or what you think may be the Laughlin ground state, but you want to check by calculating an entanglement spectrum. So the idea of the entanglement spectrum is you start from the ground state psi, and you cut your system in 2 parts, 2 complementary parts, A and B, and you calculate the density matrix rho A associated with subsystem A by doing a partial trace on the density matrix psi psi. And this can be thought of as the exponential of minus the entanglement Hamiltonian. And this entanglement Hamiltonian, if you compute its spectrum, it's what we call the entanglement spectrum. So this is very generic. So how do we get quasi-Hall excitations from this? For that, you need to do a specific type of cut. So not all cuts would give you the degeneracy of quasi-Hall excitations, but a particle cut will do that. So what's a particle cut? It means that the two subsystems I'm thinking of when I say subsystem A, subsystem B, they're not like the physical, geometrical two parts of the system, but they are in terms of number of particles. So for example, if I have a system with 4 particles, that's n, I may do a partial trace on 2 of them, na equals 2, or nb equals 2. And so I get the reduced density matrix for a subsystem with 2 particles. More practically, we do Schmidt decomposition most often rather than building the reduced density matrix, but that's the same thing. It means decomposing the ground state psi into a sum over 2 complementary Hilbert space where the psi A and psi B wave functions are orthogonal. And I find it also helpful to write down the partial trace as an integral because that helps me think of what kind of cut I'm doing. And in a particle cut, when you're doing the partial trace, the integral is over the whole system. From one, if I have a torus, it's over the entire torus. But I'm integrating over only a subset of the coordinates for the particles. If I did a geometric cut, here I would not have a product from 1 to nb, but from 1 to n, all of the particles. But then I would integrate only from 0 to L, for example, and then from L to 2L would be left free. So that's a way to extract the degeneracy of quasi-holes from the ground state, as was shown in this paper. So in practice, what that means, for example, taking again the example of the magic angle twisted bilayer graphing system that I had, I can start from the ground states, the threefold degenerate ground state, and I can compute its particle entanglement spectrum. So I had, in that ground state, I had originally 30 moire unit cells and 10 electrons. So I'm going to keep 30 moire unit cells, but I'm going to do a partial trace, so I only keep 4 electrons in that system. And this is the entanglement spectrum, which can still be characterized and labeled with lattice momenta for the reduced subsystem. But also, okay, so what's really important here is that I have a gap in this entanglement spectrum that's marked by the blue line here. And I have some number of states below the gap. That's also given by the Haldane fractional exclusion principle, the 1-3 exclusion principle. And the way to find it is to calculate how many configurations do I have of 4 electrons in 30 flux quanta. So 4 electrons in 30 orbitals that satisfy the 1-3 fractional exclusion principle. Or equivalently, I could also compute the energy spectrum of the fractional quantum Hall system with 4 electrons and 30 flux quanta, and I would get a gapped energy spectrum with the same number of states below the gap as here, so 9,975 states. So that's actually a really robust way of diagnosing topological order, because it doesn't happen by chance, right? Having a gap is what makes this robust, and then you have this number, plus or minus 1, and it's not the same number. So it's something that's that's a very robust way of diagnosing topological order. Right. So I'm done with this part of. These are basically the main ways that you diagnose the fractional ground hole ground states when you're doing exact normalization. By you basically work in the torus geometry and look at these degeneracies. There's another way which is most helpful in the cylinder geometry, and is most helpful when you're doing geometry, for example, and it's through the edge spectrum. Okay, so you know about the bulk edge correspondence. It tells you that if you have topology in the bulk, it's going to be accompanied by gapless edge states, and the nature of these edge states is in one-to-one relationship with the topological order in the bulk. And in fractional quantum hole states, this is especially true. And we can actually describe the edge spectrum by a conformal field theory. The wave function in the bulk is actually given by conformal correlators of the same conformal field theory that describes the chiral critical edge. So taking the example of Laughlin states, and this is actually the same for all Laughlin 1/m, but especially for Laughlin 1/3. Then the edge is described by a U1 conformal field theory. And the result is that this edge spectrum is a chiral edge spectrum which has a very specific shape. So the velocity for this chiral edge spectrum is actually non-universal, but what is universal is the degeneracy of each state. So here what's important is to be able to have a momentum, to know the momentum of each state. So if you need to know, you need to label your eigenstates with so here an angular momentum, so that you can distinguish this sequence. And those degeneracies are tabulated in conformal field theory books, but in the case of the Laughlin 1/m states, this is what you get. So you can use that either from the energy spectrum, and for that you need to work with an open geometry, so maybe a disk geometry, or like or an hexagon or something like this, depending on the symmetries of your lattice. Or you can work on the cylinder as well, and energetically you can actually diagnose the topological order of the ground state this way. But similarly to what I explained for bulk quasi-hole excitations, you can also work with a geometry without edges, and find out what is the edge spectrum through entanglement spectroscopy. So here, the idea is to do a physical cut. So earlier I talked about a particle cut, now it's a physical cut, where you're doing the integral over all the particles in the system, but with a reduced window. And I'm showing a cylinder here because it would be actually quite inconvenient to do it in the torus geometry, because when you do the cuts, you would end up with two edges, which would be a bit hard to read actually if you have two chiral states on top of one another. So it's actually super convenient to use a an infinite cylinder geometry, which is something we can do in the context of DMRG. Then you'll end up with just one edge in your entanglement spectrum. It's actually something you get for free when you do DMRG. And it can be shown that there's a general relationship between the edge spectrum and this entanglement spectrum. And now can show you some numerics related to that, not in moire, but in a different model, in a different channel insulator model. I believe it was in the Haldane model. It's actually from our chat today, although this wasn't planned. But okay, so this is the entanglement spectrum corresponding to the ground states at filling 1/3 for the Haldane model. And there are different colors corresponding to different charges. So one needs to focus on this light blue color. And you see that it has a chiral spectrum. It has a chiral shape with exactly the degeneracies that are expected from conformal field theory. So again, that's a super helpful way to diagnose a Laughlin topological order in using numerics, and here using DMRG. So finally, I want to end with a little summary of these different techniques. So I'm not claiming at all that I've given you an exhaustive list. There are other ways. In particular, I haven't talked about extracting the whole response. And that's a quite important way of doing that. So I've talked about hexagonalization on the torus, and I've told you there was you could extract the ground state degeneracy. It's a first signature of topological order. The reason that you want to do more than just the ground state degeneracy is that when you have a symmetry broken state, it also has a ground state degeneracy. So you need to go one step further to distinguish between those two possibilities. I've also talked about finding the quasi-hole degeneracy to the particle entanglement spectrum, and that will actually help you distinguish whether you have a true topological order or just a symmetry breaking phase. Then on the cylinder geometry, especially using DMRG, you could find out the whole conductivity, especially through flux insertion. I haven't talked about that, but that's a quite practical method that's very often used. And as well, I ended the lecture by talking about how to extract the edge spectrum from the entanglement spectrum. As I said, it's not an exclusively, but these are signatures that I find to be that the community finds to be very robust and that are typically very convenient to extract. And I'm going to end here, and thank you all very much for your attention and your questions. I'm hoping there will be more today that I can answer. So I'm happy to take any questions. Hello, can't hear anything. Hello? Okay, I can hear you again.
Yeah, sorry about that. My internet somehow just.
Oh, okay. So it was you. It was not me. Okay.
I don't know. I hope it was me. Okay, so but there's a question. Sorry
Yeah.
about that. What tools do you use for both DMRG and ED?
Okay. Very complex program. So yeah, I have a. It depends. So for ED, I have my own codes. And for DMRG, I use StanPy. So it's a program that that's based on Python, that you can find and download, and that was developed by Frank Pullman, Mike Zalatel, Roger Mong, and now I think Jonas Hauschild has done a lot of good contributions, and I think many others in these fields. So I think now it has a pretty good documentation that can be found online. So, and I think it's relatively easy to use. But I haven't used any other DMRG code, so I can't really compare.
Okay, thanks. Any other questions? So maybe I have a question, maybe on, I mean, maybe a philosophical, not philosophical, but like, so you said that, our experimentalists are going further down in magnetic field to maybe find the fractional terms later. Is there anything that you think they should be doing to do, or is there a way to avoid the problems that they see? Because I believe they see like other phases competing and so on. Is there any platform, or like is there any other twisted system, or are they all equally kind of constrained? I was going to say bad, but I'm not going to say bad. Constrained by these problems.
Yeah, it's a good question, and I was going to answer, maybe try in other moire systems. I think at this point it's really, from my point of view, I wouldn't be able to really make a statement on which moire should be best for that, and as long as you use one that has a well-defined, well-separated strand band from other bands, which is in principle the case in magic angle twisted bialeographene, aligned with hexagonal boron nitride. And there are other moire systems that in principle do that as well. So maybe there'll be, I don't know, more coming from what is it, twisted mono versus bilayer, like a single monolayer, bilayer twisted at magic angle, or something like that also has a churn number. And the main, I think the main issue, at least that's the interpretation right now, is the current experiments that still require magnetic field, is that the Berry curvature in the zero magnetic field magic angle twisted bialeographene may still fluctuate too much. I don't know, given that this is the Berry curvature, and as well as the bandwidths are parameters that are super sensitive to microscopic conditions, it's really hard to be predictive about this. And I think what we have right now is I would base my exploration more on what is already seen in experiments at integer filling. So if you already have a pretty strong quantum anomalous Hall effect with hysteresis signaling orbital ferromagnetism that goes quite far in terms of filling fraction, and that includes one of those target fractional filling fractions we're interested in, that would be a good thing to start from. But that was the case in magic angle twisted bialeographene. But okay, I think there aren't so many samples of that actually do that. So maybe there will be more, and we know there's a variety from sample to sample. So it could be that in the same moire system, this actually works just in different sample.
There's another question by Mikkel. Can you get an actual energy spectrum from DMRG, for example, for each K sector along the cylinder?
Yes, you can. So in DMRG, the way I would do this is, first of all, I would work in a basis that preserves K along the periodic direction of the cylinder. So then you can find pretty easily the ground state in each of these K sectors. And then the second thing you can do if you want more than one energy state per K sector is you can project, basically. You can project out the ground state and run DMRG multiple times. So the first time you get the ground state, the second time, with the added term with the projection of the ground state, you get the first excited states and so on. But that's a bit costly. So you could get it if that's really what you wanted, but it's also typically more convenient. If the goal is to diagnose topological order, it's more convenient to use the entanglement spectrum.
Very good. So I think there are no more questions, but you're in the Slack. So if there are more questions, I'm going to direct people there. And
sounds good.
Thank you and all the speakers of this session, and see you everyone tomorrow for a hands-on session. And yeah, so see you all tomorrow. Thank you.
Thanks.